Hey guys, welcome to part 3 of the Magnetism series. In this video, we're going to primarily explore the motion that results from a magnetic force always acting perpendicular to the velocity of a moving particle. Now, if you have not yet watched parts 1 and 2, I highly recommend going back and watching that, especially part 2, because there's some very important technical information that will help you understand the basis for what we discuss in this video. Now, in the last video, if you didn't notice, I had all my examples referenced as if the iPad was laying flat on a table with the screen facing the ceiling. This might have been very confusing for you if you were watching on a computer screen that was perpendicular to the table surface. So just read the notes carefully when you go through the video to make sure that you have the same orientation as I did when I filmed the video. With that warning out of the way, let's get into it. Let's start with an example that we used in the last video. Here I have a magnetic field directed into the screen. We represent this with the X's. I also have a velocity vector pointing up, perpendicular to the magnetic field. Now, if I use my right-hand rule, I know that I need to point my 3 fingers into the screen to mimic the magnetic field lines. I then need to make sure that my whole hand is rotated so that my index finger is pointing up or parallel with the velocity, which leaves my thumb pointing to the left. So my thumb pointing to the left indicates that the magnetic force that's acting on this positively charged proton is perpendicular to the velocity. Now, this force will not always stay pointing to the left, which is very interesting. Now, I suggest that you pause the video at this point and you think back through your mechanics knowledge to figure out what will happen or what the resultant motion will be of this particle if the magnetic force is acting always, and I add that word specifically, always perpendicular to the velocity. So hopefully you remember from circular mechanics, when we're dealing with objects that curve or have curved paths or move in circular paths, that they require a centripetal force. Now, a centripetal force is a force that is always directed to the center of the path. What's a little bit of a better description than saying it that way would be to say that the force would always need to be perpendicular to the instantaneous tangential velocity. So that's a mouthful. So let's look at this. If we see that the tangential velocity is the velocity that is always tangent to the circular arc or curve upon which you're moving, then that means that at any given moment, there has to be some force that's pulling you in towards that circular path. In other words, according to Newton's laws of motion, I would just stay moving in a straight line tangent to that curve at any point if that centripetal force stopped acting. So as long as there's a force that is perpendicular to my velocity at any moment, it will effectively pull me in a circular arc. Now, you can see from the result of the right-hand rule that the magnetic force always acts perpendicular to the instantaneous velocity of the particle, thereby pulling it in a circular arc. So essentially what we will see happen is that when a charged particle, note it has to be charged according to our findings from the last video, when a charged particle moves into a magnetic field, it curves, its path starts to turn. And if its velocity is exactly perpendicular to the magnetic field, we will see that the charged particle will effectively spin in a circle in the same place. Now, to predict in which direction it will curve once you've used the right-hand rule to determine the initial magnetic force direction relative to the velocity, you'll always, what I say, is hold your thumb and then use that as an anchor point and rotate your hand around that anchor point. So in other words, your thumb should always point to the center of the circular path. So if this was an electron and I was using my left hand, I'd hold my thumb as an axis of rotation or a central point, and I would always curve my hand keeping my thumb to the center of the path. So we can summarize by saying that the magnetic force acts as a centripetal force. Now remember, a centripetal force is a net force. It's not a specific force, but more so a category that other forces can fall within. So magnetic force is a centripetal force. Now, if you remember from the last video near the end, I threw a curveball at you. After we had been talking about a right-hand rule for several minutes, all of a sudden I introduced the idea that if you had a negatively charged particle, or an electron for example, you would use your left hand instead of your right hand. Now, that seems a little strange, but when we look at evidence and data, we see that this is actually the case. Negatively charged particles seem to turn in the opposite direction than what you would expect if you use the right-hand rule. Looking at these cloud chamber images might remind you of contrails, or the vapor trails that aircraft engines exhaust as they move through the sky. Now, the trails themselves of the particles are not the most important thing, but they are the visual part that helps us identify what path the particle took. So if I send two unknown particles into a magnetic field, what I oftentimes will look for is when they enter the magnetic field, based on their initial velocities being the same, will they either curve to the right or will they curve to the left in the magnetic field? The direction they curve then tells me their charge. Interestingly enough, you can actually also figure out the mass of these charged particles by knowing that the magnetic force is in fact a centripetal force. Now, the centripetal force will determine how big the radius of curvature is. So if I have a magnetic field like this, and I have a detector plate which lays along this side of the magnetic field, if I introduce a charged particle into this magnetic field right over here, I'll see that the particle will turn. Let's say it turns to the right. And depending on where it strikes on the detector plate, that represents a different radius of curvature. So you could extrapolate this to, say, entering several different particles that are unknown masses and unknown charges into this magnetic field, and whether they strike on a detector plate on the left or whether they just strike on a detector plate on the right determines whether they're positive or negative. Then, in addition to that, how far away from where they entered they strike the detector plate, we can also know their relative masses. So it helps to look at this from a mathematical standpoint to see these relationships. So I could set the magnetic force equal to the centripetal force. If I then substitute in the equation for each, so for the centripetal force, I would substitute in mv squared over r, and for the magnetic force, I would substitute in qv cross b. Now, very clearly you can see that v will cancel, and I'll be left with qb equals mv over r. So different things that we're able to measure in these circumstances are the radius of curvature by where the particle strikes a detector plate. We can also know how strong the magnetic field is that we choose to use based on the kind of electromagnet that we will use. Now, we'll get into electromagnets in a video or two, so just hold off on that for now, but know that we can measure B and we can measure R. Now, it turns out we can actually also measure the velocity, but we're going to use electricity in order to do that. We'll get to that in a minute in this video. Now you can see what's left is a mass and a charge. So if I move some things around here, I get a mass to charge ratio, which is equal to BR over V. Mass spectrometry actually does this kind of measurement. It's an analytical technique that measures the mass-to-charge ratio of ions. So basically what we can do is shoot ions or unknown charged and massed particles into this magnetic field, and then by getting measurements of B, R, and V, we can know the mass-to-charge ratio of the particle that entered. In order to keep the videos shorter and more manageable, we're going to end this video here. However, in the next video, we're going to think of ways that we could accelerate the particle up to a knowable speed as it enters the magnetic field. So I'm going to leave you here with a challenge. The challenge is, how could I accelerate a particle up to a desired speed? And how could I alter that speed? In other words, how do I know the speed that the particle is entering the magnetic field with? Now, if you need a hint, this portion is not dealing with the magnetic field, but rather with an electric field. So start there, come up with your own answer, then come back to the next video where we'll delve into that